Good morning, everyone. Welcome to the class. Today, I'm going to talk about backpropagation. In RNN. As I mentioned in the previous class, RNN, in my opinion, is really the first deep neural network. Of course, this is very suitable for sequential data input and sequential data output. Initially, this RNN is designed for text input. Usually, text is we can put in sequentially, and translation maybe will come out of this RNN network sequentially. So sequential to sequential translation is very good example of RNN. Of course, there are a couple of disadvantages associated with this RNN. Number one is data is input sequentially and output is sequential. So all this computational process is sequential. But human beings are not patient enough. Let's assume that we put into the Korean text and translation is English. Let's assume that it takes a minute or 10 minutes. This RNN is not suitable for commercial applications. You remember that if you are using ChatGPT, if you put into Korean language and ask them to translate, it takes just less than a second to make a translation. Then we are very happy. But in the future, by using the AI supercomputer, we want to make them work in a millisecond. Of course, in order to do that, we have to have GPU 1,000 times faster than right now, and we need a supercomputer that can do the translation in a millisecond. That means 1,000 times faster. So, transformer model, that is the evolution of RNN, is basically parallel processing. Simultaneously, they accept the input and they generate the output simultaneously. So that is the very key part of the transformer network. You can pick up hamburgers on there. Please enjoy. Yeah. And second thing is that because this is very sequential process, some data has input at the initial time step. Some of them are million time step later. So the effect of the contribution to the output at the initial stage and last stage are quite different. That is called long-term memory effect. So in order to overcome that long-term memory effect, the transformer model is using attention network. And third disadvantage of this one is that somehow it doesn't have position information at the deep neural network. So in the transformer model, we are using positional encoding method. Those three are major difference between RNN and transformer model. After the Chuseok break, we're gonna go deeply into the transformer model. But right now, let's focus on the RNN again. Especially in this class today, I'm going to talk about the backpropagation. You remember that very important and most important feature of deep neural network is backpropagation using the gradient descent. During that process, we have to define loss function, and then we have to develop the chain rule to execute the backpropagations. By using the backpropagation, we can update the model parameters, and eventually we can optimize the deep neural network. Backpropagation means we have to do a lot of backpropagation to optimize the model parameters, and also it is kind of parallel processing because it is matrix multiplications in the back direction. Because of that, GPU and parallel computing is the most important feature of the AI semiconductor and supercomputer. So to have understanding of RNN a little bit deeper, I would like to give you brief introduction of backpropagation today. Probably it makes a week or a month to show all those the sequences of backpropagation, but today I'm going to give you a little bit of that. You can pick up, okay. This is the overall architecture of RNN. I would like to briefly overview the RNN architecture again. We have an input vector at each time step. Input vector is connected to input layer at sequentially at stage 0, or actually stage 1, stage 2, stage 3, it will go to up to the final stage time t. So input will be connected to the deep neural network sequentially, time t1, time t2, time t3, and time t. And we're gonna multiply U matrix plus activation function and actually activation function as the activation function we're gonna use tangent hyperbolic function, and it's a little bit variation of softmax, not the sigmoid function. And then we multiplication of input vector and U matrix will become input of tangent hyperbolic function, and output of tangent hyperbolic function will become hidden layer vector. This hidden layer vector will be supplied to the next step hidden vector. At the time, we are going to use W matrix. And then output hidden layer will be multiplied by V vector, and that's gonna be internal vector O1. And of course, here also we're gonna use the activation function. And from our O to output Y, we're gonna use softmax. Later on, I will give you, introduce the softmax function. And then we will use the entropy function to define the loss function. So eventually, we're going to have output at terminal T. Let me introduce once again. Input vector will be supplied to the network sequentially. And at the initial stage, X1 vector will be supplied to the input layer. Then we will multiply this input vector with the matrix W, and it will go through the tangent hyperbolic function. And that is going to be hidden layer at stage 1. And hidden layer at time step T will be multiplied by V matrix. And that will be the input of activation function tangent hyperbolic. That is going to be O vector at time step T. And by having this one, we can convert OT to the actual output Y using the softmax function. And at each step, hidden layer of previous state will be supplied to the next time step, and the multiplication will happen with the matrix W. So what does this mean is that during the training process, our goal is to determine U, W, V matrix, because this matrix will be used repeatedly again and again. There are millions of elements in the matrix U, W, V. And during the back propagation, what are we going to do is to update U, W, V matrices until it reach optimal point. Optimal point means the derivative of loss function is becoming 0. Let's write it down, this RNN architecture with mathematical description. Hidden layer vector will be obtained by tangent hyperbolic of intermediate state vector Aj. Aj at time step t can be obtained by multiplication of W vector with previous hidden state. This is not very rigorous expression, but current input with mu matrix plus bias. It means that hidden state will be obtained by tangent hyperbolic of this operation. That operation is W multiplied by previous hidden state, and current input multiplied by U matrix and bias. Another equation which explains this RNN architecture is shown up in these two equations. Intermediate state OT will be obtained by multiplying the matrix V with the hidden state plus bias, and actual output function will be obtained by softmax of OT. Softmax of OT means that our output vector OT will be regularized so that summation of all these y vector should be equal to 1. Later on, I'm going to explain further. Then loss function will be defined by this term. At each output, we're going to have output at each state. At each state, each output at a time step t has a vector element. Each element has 1, 2, 3, 4, yjt, and finally up to yqt. This y function is a kind of probability function because we're gonna use the softmax. Later on, I will show you that what is softmax function. Softmax function is to regularize this y1 to yq so that all the summation is becoming 1. Actually, this y is becoming probability distribution. And yj is a kind of between 0 to 1 value. So by applying the log, that means it becomes entropy distribution. So minus means the y is the between 0 to 1, we usually have minus. So this is actually becoming a loss function at time step t. I assume and I expect that because we have been here in this class together for more months, so you easily imagine what the meaning of entropy and something like that. Specifically in this RNN architecture, they are using entropy loss function. So we can define loss at each out step will be a log summation, the entropy summation each of output. And you can imagine that if we have very descriptive output, entropy will be minimum. Like 0, 0, 0, 1, 0, 0, 0, that kind of yi distribution will have minimal loss. If you have uniform values that is not suitable for RNN output, then entropy will be usually very high number. So they keep training with different text input, different text out until they reach a minimal entropy function at the output. Then theta, that is the actually theta means W and U and V matrix will be optimized by the gradient descent method. Training of RNN means we have to find optimal theta. Theta means the parameters hidden inside WV U matrix. We have to find optimal matrix by having summation of this loss. At each time step, we have loss. Here we lost J1, here we lost J2, and here we have J3, and finally we have to JT. We have to add all together. That is this term. This term is a J at time step T. So we have to summarize this loss function from time step 1 to time step T, final stage, and summarize all together. And we have to do the certain optimization method. Usually we are using the gradient descent method or whatever. We have to find optimal theta. That is the training process of RNN. So because of that, it is a little bit difficult because we have loss function at time step T, final state. It will affect U matrix at time step 1. So we have to develop partial differential equation to make a connection between loss function at time T to the input vector x1 and U matrix. By having gradient descent relationship between loss function at time step t, final state, with respect to the first vector x1. So it is kind of very long chain partial differential equation to update U matrices. So it really takes time consuming in order to do that. In each step also we have loss function, and that to minimize the loss function we have to find U matrix by using the differential equations chain rules. It is a little bit shorter connection. But let's assume this time step is a kind of million time step. Like, let's assume that our input is a Bible, output is a translation of Bible into a certain language. Then this time step could be a million step. Then we have to apply the gradient descent and chain rule to minimize loss at the final sentence of your Bible. And this is the first word of the Bible. So it takes long differential equations. Of course, we can use the computer to do that, but today I'm going to give you a very simple example. Before doing that, we have to talk about the softmax function. Okay, let's go. You remember that, let's assume that I want to update V12. That is a connection between hidden layer to activation, this OT, there's an intermediate state. You remember that if I want to update V12 during the backpropagation, V12 has to update V12 using this equation, that's gradient descent equation. And in order to do that, we have to be able to obtain the derivative of this whole loss function, this is the J theta. We have to be able to do the derivative of total loss function with respect to V12. Very tedious job, but let me do that right now. In order to update the V12, that is the connection between output 2 to Y1. I have to develop a function to make because this loss function is a log yj, and this log we have to obtain the relationship between output and log function. That is shown up in this derivative. Also, I have to find the relationship between OT to Y1. That is the softmax function. This is entropy. This is softmax, max function. And the relationship between V1 to O1 is H2. Why is that? Because H2, hidden layer 2, multiplied by vector V1, 2, vector element V1, 2 is actually becoming the O1. The relationship between H and O is a connection V. So if you want to make a derivative of O at stage T by V, if you make a derivative, H is actually remaining. The output sequence and loss function is entropy. So this is very simplest case. So if you obtain all this equation A, entropy softmax, and C, then we have a derivative of loss function at time step T with respect to vector element V1, 2. Of course, we have to summarize them from time step 1, 2, 3 up to 10, up to terminal T. I'm sure that it is a little bit difficult to follow me at this moment, but you can, I hope you can take overall picture of this backpropagation process. This is very simple three-step partial derivative from J loss function to H. By doing that, we can update V matrix. But please remember that this is very simple case. But if you want to update U matrices, this element is affected by loss function and hidden layer at each step, and it will go back to the propagation, HT, HT-1, H3, H2, H1. It is a long step to update W. But at this moment, for the simplicity of lecture, I'm only using very simple case. Of course, right now for the simplicity of class, I'm deriving equation for V1, 2, but we have millions of vectors to do that. And that has to be done simultaneously. Let's spend a little bit more time. Please be patient. Now, I'm driving equations for these two parts together. First, we have to do the derivative of O1 with respect to loss function J. Of course, we have a minus log, that is an entropy feature, and this term is softmax function. Let's assume that you have O1t, O2t, OJT, and OQT. It's a vector. It may have, some of them may have plus number, some of them may have minus number, and actually O is such a numbers. But to impose probability concept, we apply this equation. Each O will be the input of exponential function, and we add all that together up to, we add all together, we change to exponential O1, exponential O2, exponential OQ, and that is converted to a softmax function. So summation of all this O function actually is becoming, I'm sorry, it's actually coming from hidden layer and whatever. Intermediate state has certain distributions, but we impose probability distribution. And so that this probability distribution summation is becoming 1. So denominator is actually becoming 1, and we have itself a contribution. So this whole summation is becoming 1. That is softmax function. So next step, what I have to do is the derivative O1 with respect to entropy and softmax. Then so if we apply if we move on to these derivatives, because this is log function, this is log, this term will come out, only we have this one. We have first term and we have second term. And then derivative of itself is becoming -1, and derivative of log exponential function becomes, log means this came down to denominator, and they do the differentiation of that, then it becomes itself. And very simply, log function, derivative of loss function at time step t is becoming very simple function. Why is that? Because we are using entropy function, that is a log nature, and softmax function is kind of exponential function. So having log function and exponential together become very simple arithmetic expression. So what we have to do is we have to update V12, that is the one element of the matrix, and we have to update using this equation. At the final stage here, we have H, hidden state is shown up here, and we have to make a summation from time step 1 to time step t. I think this looks very tedious and long procedures, but I confirmed it. You should believe in me. So this is the So today I gave you a lecture on overall picture of the RNN network, and I was talking about disadvantages, and also I was talking about backpropagation principles. Now I show you a simple example of V12. That is the vector element of connection between hidden layer to output layer. But another important matrix is U and W. U is connecting between our input to the hidden vector, and W matrix is the connection between hidden layers. I think this W and V might be more important. So here we gave you a very simple example, but in real case, you have to develop all the chain rule equations. Here we have three-step chain rule, 1, 2, 3, three partial derivative equation. By using the softmax and entropy equation was very simple. But we have to continue that process from final step time t. We're going to have entropy, and we're going to have a softmax function, and between them we have activation tangent hyperbolic function. So, and we have to come back and come back again until you reach to the initial input vector and U. You have to update U. So you have to develop all these chain rule equations, and you have to update U. Also, it will affect the final input vector. You have to also update U. So it takes long time to update. This is called as backpropagation through time. In some text, you can look at this concept, backpropagation through time. This means it takes time. Summation, backpropagation through time. Usually backpropagation means the gradient descent, but we have to do in each time step. That is the really killing disadvantage of this RNN. So in the transformer model, which I will give you a lecture after Chuseok break, we're going to show you backpropagation simultaneously. Input is simultaneous, computation, decoding is simultaneous, encoding is simultaneous, and attention and all. That is the very core part of ChatGPT in terms of technology, and that's why GPU and AI supercomputer are really needed. So I hope you enjoy the hamburger, and thank you, your teaching assistant, and I hope you come back with a fresh emotion, fresh mind, and I hope you have good family time during the Chuseok break. Thank you for your attention.